I'm going ahead and starting today's recording. As you can see, Blackboard has the whiteboard going today, and I have put some of math and quantum mechanics' favorite Greek letters on the screen. Before I start talking about anything, does anyone have any questions? Including homework 2, which I hope you've all downloaded. Okay. I had been able last time to start talking about operators, and I'll be up here at the top of the screen. Try this pointer out. We had talked about operators for every observable physical thing in quantum mechanics, including a position operator, which in one dimension just means multiplied by x. A momentum operator, which is essentially a constant multiplied by the first derivative of x. So this operator applied to a function takes the first derivative. This thing is often called P with a hat. So the effect of P on any function psi is to multiply it by this constant and take the first derivative. And remember, well, the kinetic energy has a constant out front. This thing and is a second derivative operator. The operator for this is often k with a hat, and the effect of k on some function f is to multiply by negative h bar squared over 2m excuse me, after taking the second derivative of f. Any potential energy in a function of x is just multiplied by that function. And the operator for the Hamiltonian is the sum of the kinetic and the potential energies. So the effect of H on any psi would be K of psi plus V of psi Now the Schrödinger equation requires specifically for something not changing with respect to time, for anything not changing with respect to time, you should be able to write H psi equals E psi. Which means if you do H to psi, and remember the operator looks to the right, what you get is the same function you started with, called an eigenfunction in this case. And the constant it's multiplied by, which in this case is the eigenvalue. The eigenvalue in this case is the energy. The Hamiltonian is the energy operator. And in the case where you do get an eigenfunction for an operator, the eigenvalue is whatever physical thing the operator stands for. The Hamiltonian is the energy for the energy the operator, so it would be the energy in this case. Questions here? Okay. We're on page 5 of the lecture handout. It's a fact in quantum mechanics that for a pair of operators, it's said it's impossible to know two observables at the same time if the operators do not commute. And the reverse is true. If the operators do not commute, you can know two observables at the same time. So the question is, does operating with A and then B have the same effect on a function as operating with B then A? Or is A, B of F equal to B, A of some function F? Now, if A and B were just numbers or even just functions, the answer would be yes, but that's not necessarily the case here. And to illustrate that, I will use, as a matter of fact, I'll jump over to the whiteboard really quick, just so I have enough room. Suppose we have two operators like the momentum operator and the position operator. And you can ask, and I'll put a hat on the position operator for now. Does it matter which order you operate? For example, the left-hand side means do X and then do P. The right-hand side means do P and then do X. If you get the same result either way, P and X commute. So let's have a look. I'll start with the right-hand side. Since P is the first derivative operator, right, h bar over I d dx, what happens first is x of P of F, and that's x of h bar over I d dx F, and I'm running out of whiteboard, so I'd like to go down but can't, so I'll come over here. and that's x, and I can move the h bar over I out front because it's just a couple of constants, and I get f prime, which, as you all know, is the symbol in Calc 1 for the first derivative of f. And that, of course, since that's just multiplied by x, means that the whole thing is h bar over I times x times the first derivative of x. Right, let me erase the steps. Get some room. Okay, like so. Okay, let's see. Can I select the whole lot? No, I can't. All right. So basically what I have shown is that doing the first thing gets you this. All right, and that's what happens when you work on the right. Now we'll work on the left. Okay, in a certain sense, it's easier to work on the left-hand side to start because the x operator just means multiply by x. So we have x times f. However, that means that we have to take h bar over I times the first derivative of x times f. Okay, both these things are functions of x. So I can pull out product rule from Calc 1, and that's h bar over I out front of f plus x times f prime. Okay, consider the result on the right versus the result on the left. Okay, I hope it's fairly clear they're not the same. In fact, the left-hand side has this additional h bar over I times f term, which does not appear in the second. Okay, so if I write, for example, px minus xp of f, the px part would give me this thing. The xp part would give me this other thing on the right. So first I'd get this, and then I'd get this, and the result of subtracting one from the other is h bar over I times f. Okay, important point about this right now is that this is not a zero, which means according to quantum mechanics, it's not possible to know position and momentum at the same time. Okay, I'm going to flip back to the lecture handout. Okay, we were here. All right, and coming down to the equation below, this gives rise to the uncertainty relation, or sometimes called the uncertainty principle. Okay, P and X do not commute, which gives rise to this formula. Sometimes this formula appears in freshman chemistry classes, or even this thing, for example, delta P is the quote unquote the uncertainty in the momentum versus, or as compared to, the uncertainty in the position. Okay, what happens is, if you remember from when we talked about wave functions, position, and it turns out momentum as well, are statistical things. In other words, they have, if they are not eigenvalues, if they have standard deviations to them. And this is the product of the standard deviations. Sorry, having trouble with this. The product of the standard deviation of the position and the standard deviation of the momentum must be greater than or equal to the value on the right. Okay, having said all that, observe that the value on the right is amazingly small. It's around 10 to the power negative 34. So in practical applications for molar scale objects, yes, you can know the position and the momentum at the same time, because the product of the standard deviations is amazingly small. Okay, please yell out or type in any questions if you have them. I guess to sort of start to make this all. Oh, go ahead, Aya.
Would
Turn
you
on your
mind
microphone.
would you mind repeating the last statement that you made? You said if the product is smaller, then what does that say about the momentum?
Oh, well, let's see. Okay, the product of the uncertainty and the momentum and the position is really small. I don't know. So suppose you're a car that weighs a metric ton moving 40 miles an hour, and the question is, where are you? Okay, if you're a car that weighs a metric ton, P is really big. And the question of where are you, well, I mean, I don't know how much uncertainty is there. The point is that you can know where you are and you know how fast you're moving with relative confidence because the product of the quote unquote uncertainties for a macroscopic object will be vanishingly small. Does that help?
Yeah, thank you.
Yeah, it's a thing that will only matter with microscopic objects. There is a formula plugger in the homework involving the two uncertainties. Try it out and see how it works for a microscopic object. And then imagine what would happen if you put in something with a mass of, a kilogram. Okay, this is all fairly weird. And the question of what it has to do with the cannonball problems is kind of questionable. To start to pull in some of the concepts in mind, I am moving on to, and this is traditionally the end of number one, a very simple model system. Quote unquote free particle. In fact, this is so simple, it's very difficult to apply. But if you want to see the equations I'm playing at, look at this link here on page 9 and see the indicated equations and examples. My discussion's a little bit different. Okay, suppose we have an object called an electron or a proton or a neutron, some sort of particle all by itself in space with no potential on it. So we write V equals 0. And it's confined to one dimension. In that instance, the Hamiltonian operator is simply the one-dimensional kinetic energy operator, which is, as you remember, a constant stuck out front. Of the second derivative operator. The mass involved is the mass of whatever the particle is. Which, to make the units come out good, you should probably put in kilograms. All right, the question arises, okay, we have to satisfy H psi equals E psi. In other words, when we operate with H, we have to get the same function back times a constant, which is the energy. Okay, this type of problem gets addressed by mathematicians and engineers in differential equations courses. For purposes of this course, what I'm going to do is show you psi. It's right up here. It's basically e to the ikx. And I'm going to ask, what is the energy? Okay, so what we have to do here is A, show this is an eigenfunction in the Hamiltonian. And it turns out it's easy to do this at the same time. Once you do that, we write down what the energy is. Okay, so here is the answer. The function has to look like this. Okay, as you see, this function has some pretty weird features. It's got a complex number in the exponent, or it's got an imaginary number in the exponent. But let's just remember we could treat that as a constant right now. And since the Hamiltonian is the kinetic energy operator, we'll just think about the effect of operating on the function. Okay, this thing over here is a constant, so we can leave this where it is and not worry about it. All we need to think about is what's the second derivative of e to the power of ikx. All right, I'm over at the chat box now. The first derivative is I times k times e to the power of ikx. I might write like that, like this. Oops, I'm sorry. Like so. Who can knows what is the second derivative? We're just differentiating exponential function. Aya has it. If you differentiate again, you just multiply by the constants in front of the x again, and so that's I squared e squared, k squared e to the ikx. Right. I'm going to write that down here on the right-hand side. First, we got the negative h bar squared over 2m. I can multiply that by the other constants, which are I squared and k squared. And I'm running out of room, but the function they're all multiplied by is e to the I x. And I can simplify that, which gives me room to write more. H bar squared, negative h bar squared over 2m times negative 1 times k squared e to the ikx. Or just cancel the negative signs. H bar squared over 2m. Oops, I forgot the k squared in the numerator. E to the ikx. Okay, the function we started with is e to the ikx. Here it is again. This is the eigenfunction. Well, it's back, so this is the quote-unquote eigenfunction. And it is the eigenfunction because this thing it's multiplied by over here to the left of it is a constant, which is called the eigenvalue. Okay, that means the energy of this thing is h bar squared k squared over 2m, where k is just a constant. We can assume k is greater than 0. We'll make that assumption. Okay, so the energy is h bar squared k squared over 2m. Even if we say k has to be a number greater than 0, that means that this energy, which is the kinetic energy, remember, because it's only the kinetic energy involved, can have any value. If you're curious about k, note, given that I is unitless and x is a length unit in like meters, the standard metric or SI value for k is reciprocal meters. So I'm putting that in the chat box. The default units for k are reciprocal length units or meters to the -1. And you'll find then if you multiply h bar squared times k squared over 2m, that you get an energy in joules. If you take the mass in kilograms. Questions so far? Okay, I'm going to try to throw one out there. And you could also ask about what's the momentum P, or what happens when P operates on psi. All right, remember the momentum operator if we're stuck in one dimension is h bar over I times the first, well, as a constant multiplied by the first derivative operator. And psi is e to the ikx then P of psi is H bar over I times the first derivative operator times e to the ikx. Okay, we have already noted that if you take the first derivative of e to the ikx, what comes out is ik times e to the ikx. Or that equals, since the i's are going to cancel, h bar times k times e to the ikx. Right. Again, we get the function we started with back, so this is an eigenfunction. Because it is eigenfunction of the momentum operator, the eigenvalue, h bar times k, is the momentum. All right, you have one of these in the homework. The k value is 9. Remember that the default units of k are reciprocal meters. The eigenvalues of momentum. We know the eigenvalue. All right. I should stop for a second. I'm about to clear the board. Are there questions before I clear the board? All right, let me try to throw something out there. I is e to the ikx. We've seen that the position operator is just multiplied by x. I'll put it out to the class. Is psi a eigenfunction I'll just finish. Of the position operator. As you can see by looking at homework too, this type of question is fair game. I like think it'll be, well, the homework has different, different operators. Okay. So yes or no, or how do we know if psi is an eigenfunction of the position operator? Pardon my typos. I hope everybody understands the question. Oh, okay. Paul Roy, okay. No. Okay. Why?
Because if you multiply psi by x, you get another function which is just x times e to the ikx, and you don't have that
That's
constant.
right. Well, that's a very good point. And x psi in this case is just x times e to the ikx. Now it's very tempting to think, oh, there's an e to the ikx right here. Therefore, must be eigenfunction. But x is not a constant. So this is not an eigenvalue. And therefore, e to the ikx is not an eigenfunction. Okay. Which sort of, well, engenders the question, or it can. It's like, okay, we can't figure out the position this way. How can we figure out what the position is? Well, one way, you remember that psi star psi is the probability distribution. One way is to plot psi star psi and see where that's, big and see where it's small. Okay, so we don't have a function of the position operator. Let's plot psi star psi. I say this first because this is the thing, always psi star psi is the probability distribution function. And so that's, well, if you're trying to figure out where things are, that's the important thing to know. I'll also point out that since psi is e to the ikx, we really don't have a way of plotting it right now in the conventional sort of sense. Okay, so let's hope we can plot the other thing so we can have some idea what's going on. We know what psi is. Next question to ask is, what is psi star? Okay, psi star is the complex conjugate of psi. Okay, so who can say, how would I write down psi star? Or just for a start, how to make a complex conjugate. Okay, if any function is e to the ikx, to make a complex conjugate, you simply take any i's that you see in the function and replace them with negative I. I should have said more about e to the negative ikx. I will say more about e to the negative ikx. I'll say it here in a second. But for right now, if e to the ikx is psi, psi star is e to the negative ikx. And therefore, psi star times psi is e to the negative ikx times e to the ikx. Okay, so the product of e to the ikx and negative e to the ikx is equal to e to the 0, which is 1. Okay, if you try to plot a probability distribution for this thing, and I'll sketch that down here. Well, here's the y-axis, here's the x-axis. One dimension is anything between positive infinity and negative infinity can be x. And if we plot psi star psi in the dashed line, that's equal to 1 in both directions forever. Which means A the particle is equally likely to be anywhere. Another way to say that is we really have no idea, or the wave function gives no idea where the particle is. Okay, so while we know the momentum exactly, we have no idea of the position. In this case, delta P is 0 and delta X is infinity in the uncertainty relation. I should have mentioned, and this will appear in the links, it's also possible for psi to be e to the negative ikx. If you let this be psi, you'll see that the energy is still h bar k squared over 2m. But you'll find out the momentum is negative h bar times k. This function has negative momentum, essentially. Whereas if psi is e to the ikx, it has positive momentum. In other words, the particle in this wave function is going to the left. Okay. I'm going to clear the page. Problem with the free particle is, as I say, although it's an eigenfunction of the Hamiltonian, in principle you have no idea where the particle is. And in most cases, we have some idea where the particle is if we're thinking about it at all. You may see that free particle wave functions are used to make time-dependent wave functions. In other words, well, where the probability the particle is allowed to move around in time. But all by itself, the free particle is not that useful in models. There's a particle somewhere in the universe, and its energy can be quantized in that case. Not that useful. Okay, I will note, however, that we have addressed every question on this handout except do H and P commute. This question may appear later. There's a similar question in homework 2. Or it's similar to the uncertainty principle example I did earlier as well. Okay, I guess I want to leave off this. This is the end of Unit 1. Okay, I want to start Unit 2, which is about model systems, by talking about the particle in the 1D box. Okay, essentially, what a model system does is find some sort of H or Hamiltonian for some particle or system solve H psi equals E psi, and if your model looks enough like reality, you get something which is pretty much like the true energy and hopefully like the true wave function of the thing. Okay, last week I talked about how the particle in the one-dimensional box is applied by Kippis to pi conjugated molecules. Okay, what we will do now is walk through this model system from the beginning and see how psi and the energies are developed. Okay, we have some particle. Imagine an electron. That's convenient. It's confined to the x-axis. In other words, it's one dimension. And the potential energy is infinite when x is less than 0 or x is greater than L, as you see from the picture. So essentially, by making the potential energy infinite, the particle can't go there. So the wave function will be 0. in these regions. Okay. In the box between 0 and arrow, V is 0. The operator in the box, since V is 0, is once again a kinetic energy operator. Okay, the solutions to this thing, H psi and E psi, are A sine n pi x over L. L is the length of the box, where n is 1, 2, 3, 4. N equals any natural. Okay, question often arises, how is this different from the free particle? And sometimes the particle in the box is often erroneously called the free particle. Well, the difference is the requirement that psi be 0 outside the box. Sorry, let me flip back. Okay, the requirement that psi equals 0 outside the box means, zooming in at the bottom of this slide again, psi must be 0 at x equals 0, and psi must be 0 at x equals L. Okay, now if you look at these sine functions down here, you will see that they meet this criteria. If you plug 0 into x, you get sine of 0, which is 0. If you plug L to E in for x, you get sine of n pi for some sort of natural number, and sine of pi, and sine of 2 pi, and sine of all the pi's is 0. So unlike the free particle, this satisfies the boundary conditions imposed by the particle in the box. Now, as I mentioned earlier, this is an infinite number of solutions. What I have next on lecture handout 3 are example exercises. Now, these example exercises are very similar to the sort of examples exercises you can and will get asked on homeworks and exams. Now, to use them, in this case, there are often integrations involved, and to do these integrals, I have provided in this case, and will typically provide or allow use of handy standard integral formulas. Here we see a number of formulas for indefinite trigonometric integrals. Okay. So if these things are going to be, moving on to the exercises, eigenfunctions of the Hamiltonian, we first have to be able to write down the allowed energies. Okay, now I will say again, this is a pretty standard exercise. Given that psi is A sine in pi x over L, and that h is negative h bar squared over 2m times second derivative operator. How would I figure out what h psi is? Okay, I'll start out with the easy part. First of all, negative h bar squared over 2m stays the same. So the question becomes, what is the second derivative of sine n pi x over L? I can bring a over here for right now. Because it's just a constant, and I don't have to worry about it when I'm taking the second derivative. Okay, what's the first derivative of sine n pi x over L? I have to use p for pi in the chat box. Cosine n pi, almost. That's great, except for almost, it would be, oh, correct. So you would write np/L cosine npx over L. Okay, great. Because the derivative of sine is cosine. Now the derivative of cosine to get to the second derivative would be what? Derivative of sine is cosine, so the derivative of cosine is, remember the negative sign? That's right. NP over L gets squared because it comes out again, and then we have a negative sine n pi x over L. So I would write, or I will write, n squared pi squared over L squared sine n pi x over L. Okay. Oh, and I have to remember, of course, the negative sign, which I'll put right here. Okay. I'm going to cancel the negative sign. And and I'm going to collect 2m and L squared in the denominator. Then I'm going to write the pi squared and the n squared. And I'm moving the a over here to write a sine n sine n pi x over L. Okay. Now, why did I shuffle all those variables out front like that? It was so I could put a nice bracket around this to show that I've got my wave function back. And since I started with the Hamiltonian, this thing over here must be the energy. Okay, in this case, in this case, the energy cannot have any value, but depends on n, which remember is a natural number. Okay, borrowing the space from I've got around here, I can take that formula for the energy and rewrite it in its most commonly observed form, this being the same form that we saw in the last lab lectures last week. Okay, because of this boundary condition, we had to use the sign functions for our solution. And that means that in the case of the system, the energy is quantized. Shortly, which is why conjugated dyes and cyanide dyes, which you'll look at later today, have absorption spectrum. Because you can go from one energy to another by sticking a photon into the system, allowing a photon and the energy of that photon to be absorbed. Okay, questions at this point? Okay. I'm running out of time. I got less than 5 minutes left, so let me erase the board. Where did I get 8? Oh, okay. Before I clear annotations, where did I get 8? All right. Let's come up here to where I found the eigenvalue for E. Okay, that's h bar squared pi squared n squared over 2ml squared. Okay, so I must be asserting that h bar squared pi squared over 2 equals h squared over 8. If you remember that h bar is h over 2 pi, hopefully that becomes much clearer because h bar over 2 pi is, I'll complete it over on the right hand side, h squared n squared pi squared over the denominator 2 squared pi squared times 2. In other words, substitute h over 2 pi n for h bar, and then cancel or simplify. I hope that helps. Okay. And now I pretty much am out of time. Okay, what are we doing? Clear annotations. We're working on exercises. Next thing to do is normalize. I have a formula we'll be using there. But there the idea is we take the function times its complex conjugate, or its square in this case, integrate from 0 to L, and because psi squared is the probability distribution function, we have to come out with a 1. Okay, but that'll be for next time. All right, anything else before I go? All right, if you have lab today, come to the collaborate area at 2 o'clock, and I will have a collaborate room set up for your research group. I'll see people then.